Approximate to each to the nearest thousand. Again, you would need a calculator for this. Now, if you can't write that small base on your calculator, you're going to need to use the change of base theorem. And the change of base theorem, you're going to change it either to a natural log, because that button's on your calculator, or to a log of base 10. If you change it to a log of base 10, you would have log 50 over log 5, and that you could type into your calculator. If you changed it to a natural log, it would be natural log of 50 over natural log of 5. But if you can type in log 5 of 50 directly, that's probably the easiest. But it's good to know how to do the change of base. If you like typing things into your calculator, then you can change the base so you can type in more stuff. Does that make sense? No, it doesn't make any sense. But if you wanted to, you could then change, right? You could change the base of this one. This log of 50 is the same as natural log of 50 over natural log of 10. Over log of 5 would be natural log of 5 over natural log of 10, if you wanted to do that. And then you could change the bases again and make it bigger and bigger and bigger and bigger. Don't do that. Okay? Just change it once. Yeah. No? The natural log thing is on your calculator. It is capital LN, and it should be right close to the log button. It's right below it. You couldn't see it. Well, it was using capital letters. That's probably why. So try both of those on your calculator. Try both of those on your calculator and see that the answer is the same. The same thing for part B. Log 8 of 6, if you can type that in directly, that's fine. If not, you might like to do log 6 divided by log 8, or natural log of 6 divided by the natural log of 8. And all of those would give you the same answers.
You said that if we couldn't do a log, we do the natural log?
No, if you can't do that with a base 8. You're always able to do this one because you have the log button on your calculator. This one that's written this way has a base of 10, but it's not written. But that's what the log button on your calculator is. What would be here? What would that be? That if you have a calculator that lets you do log bases like I have here. So your calculator, that would be under the math button, and you'd have to scroll down to the bottom till it says log base. If you push enter on that, that allows me to do log base 8 of 6. Or you can do the shortcut by going alpha y equals, go over to function, and then it's number 5 there, log 8 of 6. But you can also do natural log of 6 divided by natural log of 8 and get the same answer. You can choose either one. They'll all work, yeah. All right, questions 3, 4, and 5. Yes. All right, we are going to change the words of this one temporarily. We're going to take out the word use a graphing and insert without a. Without a calculator, I guess we have to take out the word to because it doesn't make sense. Without a calculator to graph. Without a calculator, graph y log base 8 of x. So, just like you need to know what the parent graphs of all exponentials look like, you also need to know the parent graphs of all logarithms. All log graphs have the point 1, 0. Does it make sense that all exponential graphs have 0, 1? And if they're inverses, all log graphs will have 1, 0. If the base is 8, it's going to have the point 8, 8. 8, 1. Whew. It's going to have the point 8, 1. Because if you plug in 8 for x, what is log 8 of 8? In other words, 8 to what power is 8? It'd have to be 1. Because that's what a log is, right? It's finding the exponent. So when I have log 8 of 8, I'm saying 8 to what power is 8? And the only way that would work is if it's 8 to the power of 1. So we'll have the point 8, 1. All log graphs have an asymptote at x equals 0. Just like all exponential graphs have an asymptote at y equals 0. And the shape of a log graph has the same kind of shape as an exponential graph, just turned sideways. So there's no y-intercepts. There's an x-intercept at 1. There's an asymptote at x equals 0. The domain x has to be bigger than 0. Remember the the range of our exponential functions was always y bigger than 0. Now with inverses, just x and y switch. So now it's x bigger than 0 for the domain. And if the domain of our exponential functions was everything, well, now the range of our logarithmic functions is everything. So you're going to have to do all of these ones without your calculator. So you have to know what your parent graph is, and then what we're going to add on the next page is graphs with transformations of your logarithmic graphs. Okay? So I'm going to write down number 7a here, but on page 403 you still have lots of room on that column there, right? So we're going to add some examples on page 403. We're going to graph 4 log base 3 of x plus 1 minus 5. So in order to do this, you have to recognize what the parent graph is, or what the base graph is. What's your starting point? Y equals log base 3 of x. That's my parent graph. And if that's my parent graph, just like we graphed the other one before, you're going to have 1, 0. You're going to have an asymptote at x equals 0. And that other point that I just labeled is going to be what, what? 3, 1. Good. There's our parent graph. And because our parent graph is log base 3 of x, we go to our original graph and I'm going to just highlight that's part of my parent graph, this 3 is part of my parent graph, that x is part of my parent graph. Just so that we don't get confused, since there's a number as part of our parent graph, that number 3 doesn't affect any of our transformations, because that's part of our base graph. Now if we look at the points that we're dealing with, we have the point 1 comma 0, we have the point 3 comma 1, and we have our asymptote at x equals 0. Moving from left to right, what do we run into first? The 4. What's that going to do? Affect x or y? Y. And what's it going to do to the y? Times it by 4. Is the x going to be multiplied by anything? Because we could do that at the same time. No. So I'll still have 1 comma 0, but now I'm going to have 3 comma 4. Going from left to right, my next number I run into is the 1. Remember, the 3 is part of our parent graph, so it doesn't affect our transformations. What is that 1 going to do? It's going to go left 1, and we can go up and down at the same time. Down 5. So left 1 will get this to 0 minus 5, and here this will go 2, negative 1. What's the only thing that's going to affect an asymptote at x equals 0? Moving it left or right. What do? We move left 1, so our asymptote is now going to be at x equals negative 1. Taking all of this information now, we now have an asymptote here at x equals negative 1. We've got the point 2, comma negative 1, and 0, comma negative 5. And there's our log graph. It's been stretched, and then it's been moved left 1 and down 5. Ready? I'm going to give you one to try on your own. Okay? It's going to be a little bit. Hardest one I can think of.